recap of all of this stuff. So we'll learn more about the anatomy, those of you that haven't had lab yet, in lab tonight. We're looking at the renal physiology, about how we create urine. So we're looking at first where this whole process begins at the region known as the glomerulus, which is a process called filtration. Filtration happens because of three forces that are at play in our glomerulus. We have 60 units of blood pressure trying to push the plasma out. I have my albumins and other proteins in the plasma trying to actually keep the water in as an opposing force. And then there's the actual pressure of the filtrate that actually fills up the capsular space, trying to push itself back into my glomerulus at 18 units of force. And overall, it gives us a net difference of 10 units of force pushing the filtrate out of the glomerulus into my proximal convoluted tubule. That 10 units of net force creates 180 liters a day of filtrate production. So we call that the glomerular filtration rate on a per daily basis. Or I can look at my glomerular filtration on a minute basis, which is 125 milliliters per minute. That's the one we want to focus on because that's the one our kidneys try to maintain as a homeostasis level. If my glomerular filtration rate value of 125 a minute changes, I need to do something to bring me back to normal, whether it was due to an increase in GFR, maybe up to 130, or a decrease in GFR, maybe down to 120. I have to do something to bring it back to normal. And I can use combinations of either dilating afferent or efferent arterioles. If I dilate just the afferent, more blood comes in, my GFR goes back up, I'm happy. If I just dilate the efferent, then I can drop my GFR because it's easier for things to leave with that. And other various combinations of this, which we'll look at a bit later next week. So of that 180 liters, obviously I don't create 180 liters of pee a day. I need to reabsorb as much of that as possible, as fast as possible. So the majority of our reabsorption takes place right off the bat, right after we're done filtering it, in the region known as the proximal convoluted tubule, otherwise known as the PCT. Now the reason we can get the majority of our reabsorption happening there is simply due to the basic principles of facilitated diffusion of solutes out of the filtrate. And the easiest way to see this is by simply just following sodium and its facilitated diffusion from the filtrate into the cells and from the cells into the peritubular capillaries. We have leaky channels in the membrane, and sodium simply follows its concentration gradient into the cell. I maintain that gradient by using sodium-potassium ATPase pumps, which, as Taz would also remind us, is also known as a antiporter, because we're transporting two things in opposite directions, just to see if you guys remember that term. But you can simply call it a sodium-potassium ATPase pump. It requires ATP to do it. And you've got thousands of these on the membrane, not just one. We have thousands of leak channels, not just one. So I have a lot of sodium being facilitated into the cell and pumped out. That creates a gradient for water to follow through the use of aquaporins in the membrane. And as water leaves, I lose tubular fluid volume, but it also facilitates the facilitated diffusion of all other things that are in there, such as glucose. And glucose is using what's called a sodium-glucose co-transporter, because they're both moving in the same direction, also known as a syn-porter. But this requires no ATP, but it is facilitated diffusion. That way I can get glucose into the cell. A different carrier then takes it out of the cell and allows it to enter the blood. All right, let's then, before we get to this part, anybody have any questions? Anybody has anything? It seems like a wedding. If you don't speak up now, I'm going to marry you to the concept and move on. I'm happy to say something else different if I need to. But you guys, I depend upon you guys saying, I'm screwed, I don't get it. I don't get this at all. Why is this happening? If you guys don't say anything, I assume you get it, and the responsibility is on you to say, hey, dude, I'm sorry, I feel embarrassed, but I don't get it. And if you feel embarrassed, guess what? Somebody else is be glad that you said it, because they're just as embarrassed as you are. There's no reason to be embarrassed.
Just to make sure I'm orienting right, the tubular fluid, there is with,
That stuff right there.
right there, okay.
Yep, it's the fluid in the tube.
Got it.
Okay.
Thank you.
JJ, you all right?
So good,
You're so good, huh?
so good.
I'm so wide awake, John. Okay, let's get to the next part. The loop of Henle. Scott, what was that?
Oh, he was raising his hand. I was just gonna ask, what makes it constrict or dilate when it needs to change the...
We'll get to that. All right, we will talk about that on Monday. There'll be chemical signals and hormones that are going to do that. All right, now we're getting to the loop of Henle. Now, as I look at this, right, I realize that it's comprised of two major sections that we'll learn about in lab tonight, a thin descending and a thick ascending. But half of the water that is left, right, so when we do all this filtration, right, of 108 liters of water, the remaining part, about half of that water, we're going to reabsorb along over here. Now, the thin descending is made of simple squamose. It is only, and you want to capitalize that, permeable to water. That is it. Therefore, what is it not permeable to? Any other solid. The thick ascending is not permeable to water. It is not permeable to water. We will do facilitated diffusion of sodium and chlorides.
Is it what tissue?
Well, it's going to be simple cuboidal. Let's take a look at that. That's what this picture shows us. And you'll be more familiar with this once you get maybe the anatomy notes tonight. But there's my thick, this part right here where the word 300 milliosmoles is. See how wide that channel is? That represents our thick segment, right? We're looking like right there. Then it kind of narrows like a tapering. So this is simple squamose. There's the water leaving. And what happens to the concentration of the filtrate as water leaves? It's getting more and more concentrated, not bigger. Water isn't getting bigger, but it's getting more concentrated, right? And here's a simple way you realize this. How do you guys intensify the flavor of a sauce? You don't add more sauce.
That's what I did.
Dave, what do?
You boil,
You reduce the sauce by boiling off the water, right? Removing water increases concentrations. We're simply removing the water from the filtrate into the neighboring tissue. Now, nobody say anything. Let's put it over here. If this is my thin descending right here, and I guess I'll use blue for water. And I've got H2O right here. And let's say right there it is also 600 milliosmoles of concentration, right where my water is. Maybe to really drum that in, I'll do it like this for you guys. Sorry, it's kind of a work in progress here. If I do 600 here, it's wet, it's gonna make a mess. And there's my water. Let me repair my tubule here. Nobody say anything. Nobody say anything. Now, why is water leaving and going into this tissue space? You know why. Why is water leaving the filtrate and going into the neighboring tissue? Because this is simple squamose. It's easy for things to move through. There are aquaporins here. But why would water be going from here to here? All right. You should know that right now. And the answer is higher, lower what? Is there more solutes here than here? Or more water here than here? What are you talking about? More of what? Solids or water?
water.
Exactly. There's more water here than here, which means the concentration of this, is it more than 600 or less than 600?
More.
Less. More than
More.
600.
How many say less? Raise your hands. How many say more solutes? The majority wins, right? It has to be more hypertonic, right? Water always goes to the more hypertonic environment. So let's just make it 620, all right? There's more water here than here, but there's more water here because there's more solutes here. That's why water keeps leaving, because as the tube goes down, the tissue is getting greater and greater in concentration. So maybe there's 620 here, 720 here, 820, 820 here. It just gets more and more concentrated the further down we go. That allows us to continually let water osmotically leave. It's just simply always going, so if there's 900 here, then you want to have 910 over here. It simply just always goes to the more hypertonic environment. We then turn the corner, that's about the maximum concentration, about 1200 milliosmoles. Then we start going back up, and I look at this and go, all right, I can see how it's becoming more concentrated because water's leaving. Then why in the hell is it getting more and more dilute? Because now you're pumping solutes up, exactly. It's like being able to go and remove salt out of water. The water gets less and less salty the more salt I take out of the water. And here they're showing you the two ions that are being taken out of that filtrate are sodium and chlorides. We have to look at how this is actually working, though. Because this is the thick ascending portion, which remember I said is impermeable to water. This, remember, was only permeable to water. There are no solutes leaving here, but there's no water leaving over here. Let's zoom in on it. So this is the same thing as this. We're looking right here. There's the apical side of the cell. There's the basal side of the cell. There's the lumen, right, with the tubular fluid. This is a co-transporter. It's moving 2 chlorides, 1 potassium, and 1 sodium together. And as you get more astute at this, you should be going, oh God, that's really freaking cool. There's no change in membrane potential. 2 negatives and 2 positives. You should be like, you should be really impressed. Okay, you're not, all right. Let's follow the path, though. How can this work? This requires no ATP. This is just pure facilitated diffusion. I bring in 2 chlorides. They get transported out by a symporter that moves chlorides and potassiums. That's how I get the potassiums. I maintain the gradient by simply facilitating their diffusion on the basal side. Here comes sodium. How can I maintain sodium's gradient to always want to come in? Well, here I'm using a sodium-potassium pump. Your infamous 3 sodiums, 2 potassiums, even though they're not showing you the numbers here. That way I can always maintain the ability to have sodium diffuse into the cell. It then gets pumped out of the cell. Remember I said pumps are always on the basal side. But if you look at this, you realize, wait a minute. Well, how old your horse is here? Potassium is facilitated its diffusion into the cell. It's facilitated diffusion out of the cell, and then we rudely pump it right back into the cell, and it leaks right back into the filtrate. It made a round trip. Mm-hmm. So really, the only 2 ions that are leaving the filtrate are what? Right, which is why they only showed those there. There's actually no net change in potassium. They're just showing you the 2 ions that actually do literally leave the filtrate. Right? But now we know how they're actually leaving. It's a transporter that uses 2 chlorides, 1 sodium, 1 potassium. We have a pump on the basal side to maintain the ability for sodium to come in, and we pump the potassium right back in again through leaky channels in the apical membrane.
That's really our 3 and 2 pump, right?
Yeah, like I said, it's always 3 sodium, 2 potassiums. They're just not showing you the 3s and the 2s.
So for potassium to come from the tubular fluid into the cell, there's no ATP.
No, that's facilitated diffusion.
Okay.
Remember diffusion, bless you, requires no ATP, whether it's simple or facilitated.
Okay.
All right, now let's get to the distal convoluted tubule, where we have both reabsorption and secretion. Little footnote, the distal convoluted tubule's main job is actually secretion. It'll do a little reabsorption under normal conditions. That's our caveat. Under normal conditions, the distal convoluted tubule does mainly secretion with a little bit of reabsorption. All bets are off and things get wonky. Now, to do that little bit of reabsorption, we have two hormones at play. We have ADH and aldosterone. Oh God, do I ask? What cells produce ADH? Very good, the SONs. You guys should remember that. Where are SONs located? Hypothalamus. Where they release their hormone? In the post-pituitary. Where do I make aldosterone? Very good. Now here's how you can remember it. We're talking about the kidneys, right? The kidneys have a glomerulus, and we're using the zona glomerulus to produce aldosterone, which plays a role in renal function. Oh, God, yes. Now, what does aldosterone do? Aldosterone will put more sodium and potassium leak channels. You guys should be writing this stuff down. Even if you're recording, you should write. Sodium potassium leak channels in the apical membrane and ATPase pumps in the basal. Your sodium potassium ATPase pumps. So more sodium potassium leak channels in the apical membrane and your friendly sodium potassium pumps in the basal membrane. That's what that hormone does. Let's see how this works. So now, bless you, right? They are showing you where we are looking in our renal tube structure. It's the purple area. And it takes a bit of practice, but I realized there's my proximal convoluted tubule. You're talking about 108 liters of water being reabsorbed up there, and glucose transport, all that fun stuff. Then there's my thin descending, only permeable to water. There's my thick ascending, only permeable to sodium and chlorides. Oh, that does remind me, I forgot one thing. Sorry, ladies and gentlemen. Let's back up just a bit. Put this on pause. Let's back up, let's back up. And go back to slide 12. Look at the concentration of the filtrate as it enters the thin descending. Right? It's 300 milliosmoles. By the time we leave the thick ascending, it's at 100 milliosmoles. Now, nobody say anything. Which one has more water, the 300 or the 100? I thought I said nobody say anything. Oh my goodness. Right? This has more water. This is a more dilute solution. That's really important to keep in mind. Right? That is a very dilute solution. We're going to use that diluteness if you're dehydrated. And if you're not, we're going to pee it right out. All right, now we can get back to my distal convoluted tubule, where my filtrate is at 100 milliosmoles at the beginning of this purple region. And all this, well, most of this purple is going to be distal convoluted tubule. So I look at the picture, and John always says, don't look at it, look at it. Pay attention to it. Focus, look at it. I realize they've got two different things going on here. Right? There's this anatomical right side, right, and then the anatomical left side. Sodium and chloride reabsorption in entire distal convoluted tubule. Right? Remember, reabsorption means to go back into the blood. All right. So there is a co-transporter, and I'm simply doing facilitated diffusion of sodium and chloride out of the filtrate into the cell. There's a leaky channel for chloride, so it can simply diffuse into the cell. And there's my little friendly thing that gets to drive the whole damn thing. Your friendly neighborhood Batman. The sodium, potassium, ATPase pump. Always 3 sodiums, always 2 potassiums. And all I'm doing is maintaining the ability for sodium to diffuse in, and that drives this.
But in this case, it's drawing potassium out of our tissue to do that?
Not out of your tissue, but out of your blood.
Out of the blood,
Yeah.
out of the body.
Right.
So we're losing potassium at this.
Exactly.
It's not doing the round tripping.
Nope, not at all. And actually, you're getting to the next point in a minute.
Oh,
But that's a
sorry.
good option. No, you're fine. You're doing good. All right, so I've got sodium leaving, right? And what they should have done is they should have put a potassium ion right here for you. So put a potassium in the blood. That'll be pumped into the cell. And then it diffuses into the filtrate. And if you notice our net change in ions, sodium leaves the filtrate and goes into the blood, and potassium leaves the blood and goes into the filtrate. It's a sodium-potassium exchange. The more sodium you reabsorb, let me ask you this, to give you guys a chance to write that down first, right? Sodium goes into the blood, potassium leaves the blood, goes into the filtrate. Look at the picture when you get a chance for a second. Am I reabsorbing sodium in that diagram? What's the definition of reabsorption, right? From filtrate into the blood. What am I doing to potassium? Am I reabsorbing it?
No.
What term can I use for it? We're doing secretion, right? We're secreting potassium into the blood. So sodium reabsorption is followed with potassium secretion.
We're secreting potassium to the filtrate,
Yeah, not the blood.
not to the blood.
We're secreting it from the blood.
Yeah, you said to the blood.
Yeah.
So from the blood to the filtrate for potassium, from the filtrate to the blood for
Right.
sodium, right?
I might have said, might have tied too closely with the sodium pause. So sodium into the blood, potassium into the filtrate. That's normal, right? Now, look at the next diagram. Sodium-potassium exchange, which we just talked about, right? In aldosterone-sensitive portion of the distal convolute tubule, right? And collecting duct. In other words, the distal convolute tubule is sensitive to the hormone aldosterone. What does aldosterone do? Well, we just told you what it does. It puts in more sodium and potassium leak channels in the apical membrane. So in your mind, you're drawing little sodium-potassium leak channels up here. It's not an exchanger like they're trying to show you here. The idea is roughly the same, but they're not using the right protein structures. So you got sodium leak channels, potassium leak channels. Now you've got more sodium-potassium pumps that are here. Those are your normal sodium-potassium ATPase pumps. That drives the whole thing. It allows me to have more sodium go from the filtrate into the blood. It also allows me to have more potassium leave the blood and go into the filtrate. So I've got more leaky channels on the apical membrane and more pumps on the basal. That means the more aldosterone you have, the more sodium you reabsorb, and the more potassium you secrete into your filtrate. Let's just see if we can make a little mental connection. What do you know about potassium? What do you remember about potassium? Especially since the last exam. Where do you remember potassium playing a role in anything? Action potentials of what?
Muscles and nerves
Okay, what muscles are we talking about? Maybe cardiac muscles?
on the last.
Does potassium play a role in your membrane potentials of autorhythmic cells? Of your contractile cells? So if my blood potassium levels go off, then might the function of those membrane potentials go off?
Yeah.
Exactly. Right, this can be a problem for us. We're going to talk about later on. Right, how much potassium you lose could be detrimental to cardiac function, especially your arrhythmic and contractile cells. So we got to be careful of how much aldosterone we actually secrete. Now, if I am dehydrated, this is actually very beneficial because I can bring sodium in from the filtrate into the blood. And what are they not showing you that's going to be following the sodium? The water, right? So the more sodium I reabsorb, the more water I will reabsorb as well. They should put it in this conversation because this is only about what aldosterone does. But since we're talking about it, let me add another idea to your head. What does ADH stand for? Anti-diuretic. What do diuretics make you do? They make you pee. So an anti-diuretic is to make you pee less by reabsorbing more water. How does ADH help you reabsorb more water? By putting more of these in the cell membrane. ADH causes an increase in aquaporins. So if I have ADH released, I'll put more aquaporins in. That allows me to reabsorb more water. If I have aldosterone being released, that puts in more sodium, potassium leak channels and more sodium, potassium pumps. Bottom line is more aldosterone, more sodium gets reabsorbed. That causes the water to want to follow that more sodium. So we generally have both aldosterone and ADH released at the same time because they work kind of together to help us maintain blood volume. All right, so bottom line, right, in terms of the distal convoluted tubule, is you're looking at potassium secretion, right? That's this, right? Potassium leaving the blood, going into the filtrate, right? In exchange for sodium reabsorption. We're next going to talk about hydrogen secretion due to sodium reabsorption. That's going to be this right here. Now don't freak out like, oh my God, look at all this crap. Let's just follow the hydrogens for the moment. So there's my filtrate. This is my cuboidal epithelial cell of the distal convoluted tubule. Here's my peritubular capillary. And so let's just kind of look right down here where I notice this, and there's a nice little sodium hydrogen pump. Okay, it's pumping sodium out and pumping hydrogens in. All right. So where does that hydrogen go? Let's just follow it. That hydrogen would go to another exchanger where I can then remove the hydrogens into the filtrate and I can bring sodium in. So basically we have, to keep it simple for tonight, as sodium is brought from the filtrate into the cell, it is then transported out of the cell into the blood, and we are exchanging that with hydrogen ions. So the hydrogens will leave the blood, go into the cell, and leave the cell, go into the filtrate. So the more sodium we reabsorb, the more hydrogens we will secrete. We are ignoring the ammonium chloride path. Right, don't worry about any of this over here. Right, worry about none of this, none of it at all. It does not exist to you. Right, and we're not even going to worry about your friendly little equation I told you guys are going to see over and over and over again, right? Not going to worry about it either, right? We're simply just following the idea of sodium reabsorption is followed along with hydrogen secretion. The one thing we do want to add is the sodium that's in here, right where I'm pointing to now, those little dotted lines of sodium, your cell doesn't know and doesn't care where the sodium came from. But the more sodium that's in here, the faster this exchanger can work. Right? The more sodium that is in the cell, the faster the exchanger can work. How can I get more sodium into the cell? By maybe using aldosterone. Right? Remember that puts in more sodium potassium leak channels in the membrane. With more sodium coming in, this pump can work faster. If this pump works faster, more hydrogens get to leave the blood and go into the filtrate. What happens to the pH of your filtrate as more hydrogens go in there? It's going to go down, right? It becomes more acidic. What happens to the pH of your blood as more hydrogens leave the blood and go into the filtrate? It becomes more alkaline, right? And it can be driven or influenced by aldosterone. Because the more sodium in, right, the more that pump works. It doesn't care where the sodium or how the sodium got in there. It just says, oh, lots of sodium, I'm going to work my ass off and pump it all out, and I exchange it with hydrogens. And the hydrogens go into your filtrate, which makes it more acidic and makes your blood more alkaline. So increase in pH, decrease in pH. All right. I think that's enough holy shit for the night. Okay? Now we are definitely in another region of, please, one slide at a time. Don't try and read 3 or 4 slides at a time. 30-minute, 10-minute breaks. At the end of 2 hours, now look at what study guide questions you can ask. You got to go slowly with this stuff. You're looking at one piece of the puzzle, and then another piece of the puzzle, and the picture is going to get slowly more and more clear. If you are having trouble with this, if you can bribe somebody to cover your shift, get your bodies to lab on Saturday. I'll be happy to walk you through it.